All right, so we've defined the Lebesgue integral in its most general sense in the previous section. We'll spend a little time looking at some properties of Lebesgue integrals throughout the rest of this chapter and a little bit of the next. Section 4.5 is called Countable Additivity and Continuity of Integration. And these are terms we've associated with Lebesgue measure before. Countable additivity and continuity are properties of Lebesgue measure. And here we're introducing sort of a parallel behavior for Lebesgue integrals. As the book states, these properties have no counterpart for the Riemann integral. Riemann is fairly constrained of only integrating over intervals, and we're taking full advantage of nested sets when we do the continuity, countable additivity of sets when we deal with the countable additivity of integration. And specifically, what the countable additivity of integration is, states let f be integrable over set E sub n equals 1 to infinity, a disjoint collection of measurable subsets of E whose union is E. Then the integral over E of f is the sum from 1 to infinity of the integral over the E sub n's of f. Countable additivity, given this summation, this series, if you like, right here, what we've done is taken set E, disjoint collection of measurable sets, and we've taken E and written it as a countable disjoint union of measurable sets. And to integrate over E is to integrate over each of those constituent sets and then sum them up. So countable sum, additivity, countable additivity. And the big hypothesis that will make it work is f is integrable. We'll apply the Lebanese-Dominated convergence theorem from the previous section to this. So let's look at a proof. Okay. For n a natural number, define f sub n to be function f given times a characteristic function chi sub n. What we mean by chi sub n is sort of a partial sum on the countable union of those indexed sets E. We'll take a finite union from k equals 1 to n of E sub k. So take chi sub n to be the characteristic function on that set. Notice in particular, when n approaches infinity, we're adding in more and more of these sets. In the limit, we get the union of all of the sets, and the union of all of the sets is set E, whose union is set E. So we'll integrate over these sort of partial sums of the countable union. We'll use additivity on that. We'll have to deal with a limit somehow or other. The integrability of f will allow us to deal with that limit using the Lebanese-Dominated convergence theorem. F sub n, so defined, is measurable and it's integrable. Exercise 4.28 in the exercises will take care of that. It's effectively f sub n is the restriction of function f to this union of this finite number of e's. So we get that the absolute value of f sub n is less than or equal to the absolute value of f throughout set E. Okay, so this will allow us, since f is integrable, this will allow us to use the Lebanese-Dominated convergence theorem. Now this is true, we just need to check a couple of points. If we take x in the union of the first n E sub k's, then we get these functions to be equal to each other. For such an x, the characteristic function on this set, characteristic function is 1 on that set, so the function values are equal when we choose x in that finite union. When you choose x outside of that finite union, the characteristic function is 0, f sub n is 0, and 0 is less than or equal to the absolute value of f. So in either case, we can draw this conclusion on the inequalities. Function f is hypothesized to be integrable. So the Lebanese-Dominated convergence theorem applies to say the integral over E of f is the integral over E of the limit as n approaches infinity of f sub n. As we observed moments ago, the limit of the f sub n's is the f function. So that's just a substitution there. The Lebesgue-Dominated convergence theorem is when we'll bring this limit outside of that integral. So right there, that equal sign is where we've applied the Lebesgue-Dominated convergence theorem. Integral of the limits is a limit of the integrals. So we need to address this integral of f sub n. The e sub n's are disjoint, so we can apply finite additivity. Guess that was corollary 4.8. The finite additivity to these. And if we integrate over e, f sub n, that's equivalent to integrating the f sub n, integrating f times a characteristic function, if you like. Now, what we're getting out of this then is integrals over this set of the f sub n's. This is, effectively, because we've got 0 elsewhere, we've stated, it's probably in this problem 4.28, this is a restriction as well of the f sub n function to this set here, but it's 0 outside that set. We're integrating f sub n over this set as a finite union. When we integrate over a finite union, additivity and induction tells us we can sum. So we get the summation there. That's where we're using the additivity on this. Now we want to talk about function f, not the f sub n's ultimately. And f sub n and f, they agree on the e sub k's, at least for k equals 1 to n, they agree. So we can replace the f sub n with the f function. So we've got the integral over e of f equals the limit over e of the f sub n's, integral over e of the f sub n's. So that's this first statement. We've seen that the integral over e of the f sub n's can be written as a summation. Integral over e of the f sub n's is this summation. So we'll substitute that in here. All right, now we've got a limit of finite sums, partial sums. Limit of a sum from 1 to n, limit as n approaches infinity, becomes a series. Definition of series. So we get the integral over e of f to equal this series representation on the right, and that's what was claimed. So we have not only finite additivity, but countable additivity in this setting, well, for integrable functions. So no constraints on function f other than it be integrable. Back to the notes. An additional result, continuity of integration, and that's it for this section. The proof of this result's left as an exercise in the book. Hypotheses are let f be integrable over e, and in part 1, we assume we have e sub n is an ascending sequence of functions, an ascending countable collection of measurable subsets of set E, that is, are nested in this sense. Then the claim is the integral over the union. Well, when you have nested sets, in that sense, when you have an ascending sequence of sets, the union of all those sets is defined as the limit as n approaches infinity of E sub n. This is simply the definition of this limit of sets. And the claim is you can bring that limit outside. We've got continuity with respect to the Lebesgue integral. I can take limits in and out. Not dealing with sequence of functions in this, I wouldn't call this one a convergence theorem. Dealing with the fact I can pass limits under these hypotheses in and out of the integral. Now the limit actually comes out of the set over which we're integrating. But that's the claim. Secondly, if we have a descending sequence of sets, that is E sub I plus 1 is a subset of E sub I, all these are measurable. In that case, the intersection of all those sets is defined as the limit of the sets. And the claim is when we integrate over the intersection, function f, that is when we integrate over the limit of that sequence of sets, function f, we get the limit as n approaches infinity of the integral over the E sub n's of f. So we brought the limit outside of the integral again. And when you bring limits outside of derivatives and integrals, I'm kind of thinking in terms of, when I bring limits outside of functions and integrals, I'm thinking in terms of a continuity type thing. or measure. I guess we wrote limits out of measures as well, which is a function. So continuity of integration is simply the fact that I can bring limits in and out of the integration process. Needs context. This only makes sense to have these limits of sequences of functions when we have ascending sequence of functions or descending sequence of functions. And that's it for this section. So a petite little section. We'll now look at some of the other properties of Lebesgue integrals and some coverings and things in the next few sections. I will see you there. Have a nice day.